So section 9.4 has us working with rectangles, triangles, should be a comma here, and trapezoid properties. Now, a big portion of this section is just here's a whole bunch of equations. Um, there's not much to say about it beyond that, other than here's a bunch of equations. We need to remember them, have them memorized, and or have them written down somewhere for ourselves. So that's the big overview that we're going to see in this section and some definitions and properties more than anything else. So we'll start with the rectangles and parallelograms up here, and we have our main definition of those, the parallelogram anyway. So it's a quadrilateral with, meaning it's got four sides to it, and it has opposite sides that are congruent and parallel. We can ignore the 10.4, so that was from a different set of lecture notes, so that's irrelevant now. So what that means is if I'm looking at the two horizontal sides of this parallelogram, these two things are the exact same as one another. They are congruent and they are also parallel, meaning if I were to draw a line between them, I would create a 90-degree angle right at those points of intersection. So just some kind of fun facts we have about that one there. The same thing can also be said about these slanted lengths on the sides of the parallelogram as well. If I were to put a line from this edge to this edge, I would create a 90-degree angle between those, and they would also be parallel and therefore intersecting line being perpendicular like we have here. So just some baseline definitions of what these things look like. You can also see a parallelogram depicted as a rhombus, which is this exact same thing, but all the side lengths are the same as one another, just slightly slanted as well. Then we have our two main other terms that are showing up and that we'll be seeing for rectangles, triangles, trapezoids, all these different things. The idea of the perimeter and the area. So the perimeter is the distance around the figures. That's if I were to add all of the external lengths together, what would my overall perimeter be? This holds true for parallelograms, it holds true for triangles, it holds true for trapezoids. The perimeter is pretty much the outside edge added together for every single shape that we are working with. We just start to see that term show up in the 9.4 material. Now, the other one that we have with that is the area of a shape. And again, the area isn't limited to just rectangles, triangles, and trapezoids. We see this with squares, we see this with rectangles, we see this with circles. And the area is the amount of space that is contained inside of that two-dimensional figure, meaning it's the area inside of all of this and how much space is inside that. When we are writing an area, it should be noted that we measure the area in what's referred to as square units. So let's say I'm working with inches. I would write it out as maybe I have 42 is the area. Well, I would have 42 square inches as the area, or I'd write it out as inches to the second power. This exponent does not affect the number. All it does is denote that I'm working with a two-dimensional space versus the perimeter, which is a one-dimensional space. So the area takes the length and the height into account, or length and width into account, versus the perimeter just takes a distance and adds that together. So it's kind of the subtle differences between our perimeter and our area with our units and how we see that written out. Now, as we're diving into some stuff with the actual parallelograms and rectangles, the main thing that we need to note is that we have one main equation that we are using, and that is that the area is equal to the base times the height. This is also sometimes written with rectangles as the length times the width. So the formula can change slightly based on the textbook you're looking at or the Google search that you're doing. But at the end of the day, it's going to be the base of something times the height of that thing as well. We'll see some examples of this because there are some weird ways that the height can be depicted in parallelograms and rhombuses, or rhombi, I should say. But at the end of the day, we are going to be using this one equation the whole time. So I think it's very useful when we see problems like this, as listed in our third bullet point here. Identify the base, identify the height, and or identify the area that you have been given, sometimes the perimeter as well, but identify what you've been given and then use those given values to solve for what's left over. So as we see here, I have the area, I have the base, I have the height. Maybe in a problem, I'm given the area and I'm given the base, and I need to solve for the height. Well, I would identify that for myself. I may make a quick note to the side. Here's my area, here's my base. My height is unknown. Plug those area and base numbers in, and then I solve for h. Nothing particularly crazy compared to some of the other stuff that we have done this quarter. I think this is actually pretty similar to our, I want to say it was the proportions problem. We have that the amount, the base, and then the percent, just plugging things in with what we know and solving for what's missing. Very similar idea here. So we'll take a look at a couple examples with this later on. I do want to go through the vocab and the equations for things first, and then we will jump over to more examples and go through those. So jumping into triangles, because there's a whole section on these, and I'm going to try and get all of this in one part on the screen, hoping. There we go. Okay, so triangles. We have a lot that's going on here with triangles, and at the same time, it's kind of not a whole bunch as well that we're going to need to really, really worry about. So a lot of this, again, definitions of things. We have some previous definitions coming back, our congruency, what that represents, our interior angles and exterior angles, which we covered yesterday. We have the triangle angle relationships. Remember that the sum of the inside angles of a triangle are always 180 degrees. No matter which of these types we're working with or combination of these types, the inside angles always add up to be 180 degrees. No exception to that. And now we get to our actual classifications for triangles. These are the new things that we have. We can have combinations of these as well. The main ones we want, we'll start with looking at the angle length, so the angle measures with these is some way we can look at them. So if we're looking at this based on the angles here, this right-hand column, we have acute triangles, we have obtuse triangles, and we have right triangles. So acute triangles are all of angles that are acute, meaning everything is less than 90 degrees. We have obtuse triangles, which means that one of the angles is obtuse. So one angle is greater than 90 degrees. We don't care about what the other ones are. We just care that one is greater than 90 degrees. And then our last one that we have is for right triangles. And this tells us that exactly one of the angles is exactly 90 degrees. Yeah, no problem with the GI stuff after class. Yeah, we can talk about it. So those are our three main classifications for triangles based on the angle lengths that we have been given. Now, we generally use these along with the side length classifications as well. So we would have something like an acute equilateral triangle or an obtuse isosceles triangle or a right scalene triangle or something to that effect. We use both of the terminologies that we have here and just classify that as the overall triangle itself. So we'll dive into these ones here, and we have three types for this as well. So we have equilateral triangles, and this is a triangle where all of the side lengths of the triangles are congruent. They're equal to one another. We see this most often depicted when we're looking at a triangle, and we see these little dashes showing up on the side lengths with it. What these mean is any side that has the same number of dashes on it is of equal value to this side length here. So this bottom one has a single dash going through it. Any other side length that also have a single dash going through them are of equal length as well. I may not know what that length is, but I know that they are indeed equal to one another. So with an equilateral triangle, all three side lengths are the same. They are congruent to one another. We then get into isosceles triangles, which are triangles where I have two of the side lengths that are congruent to one another. As we see with our example here, I'm seeing this line has a single dash through it, and this line has a single dash through it, meaning this side length and this side length, whatever they are equal to one another. They are congruent. This bottom side length, I don't know what it is, and I can also say, well, I don't know what it isn't equal to these other two side lengths because it doesn't have that dash through it. So some subtle distinguishing things that we will see on pictures if we are not given exact number values denoted alongside these things as well. And our last one we refer to as scalene triangles. And scalene triangles have no side lengths that are congruent to one another, meaning every side length is different. Now, this is sometimes denoted without having any of these little marks in here at all. Sometimes it's denoted with showing three different marks on the side lengths. Sometimes it's denoted with just showing this has a number, that has a number, and that has a number to represent the side lengths. But as we're seeing with the scalene triangle in this picture here, this side length has a single dash through it. This side length has two dashes through it, and this one has three dashes through it. So do any of them have the same number of dashes? No, they don't. So they don't have the same number of dashes, meaning I don't know if any of them have the same value, and I don't know what those values are. So there's no congruency and no equivalency with any of the side lengths. And again, this can be denoted using lines, this can be denoted using numbers, or it can be just left blank for scalene triangles. If you are not told about anything having side lengths being equal to one another, absolutely never assume that they are. If a problem doesn't state anything as being equal or having an exact value to it, then do not assume anything with that. If that ends up being the case where, hey, I end up having an isosceles triangle here, awesome, that's fantastic. We deal with that when it shows up. But let that happen in the problem as we're solving it versus trying to force that into place as we go through and solve these problems. Okay. So looking here. Yeah, got our next part here. So I'd recommend for everyone, if you need to, I'll leave this up on the screen for a second, but I would recommend taking a picture, either using your phone with a quick screenshot or a quick picture of the screen, or using your whatever device you're using. If you're on a computer, take a quick screenshot of the little diagram that we have here, because these are the classifications that we are going to be using in examples here in a little bit for classifying these things. All right, so our equations with triangles. These are the main ones that we are going to be using for this particular section. We covered a couple others yesterday, but a few more just to round out the group and everything. So we have our equation for the area of a triangle and for the perimeter of a triangle. So this comes from the idea of a triangle being half of the area of a parallelogram, hence the area, base, and height coming in as well. So B is going to represent the base of a triangle, H is going to represent the height of a triangle. Now, a big warning to everyone, if you are writing notes down with this, which is hopefully what you're doing, please put some red stars around this because this warning has cost a lot of people a lot of headache. We don't do this and just want to note it now for everyone. If you are computing the height of a triangle or trying to determine what is the height of a triangle, make sure that it creates a right angle with the base or you're going to get errors showing up. So what I mean by that is if we look at our triangle here, we have this one with A, B, and C as our side lengths. A lot of people want to think, oh, well, C looks like it's a side length, so I can use that for the height. Or I can just use A for the height here and then use B for the base because it's on the bottom. And that's not how the base and the height works. The way we determine the base and the height is we want to be on the lookout for a vertical line that's denoted normally inside of a triangle, but sometimes outside of a triangle. And we have a right angle that forms along that height. The right angle is the giveaway. Hey, this line here is going to be my height, and the side that it touches, in this case B, that is going to be used for the base of this thing. So the height is the vertical line with a right triangle in it, or the right angle in it. The side that it touches is going to be the base, and that is what I'm going to plug into my area equation. It might seem a little nitpicky. It might seem kind of like, well, couldn't I just use anything if I wanted? And unfortunately, no, we cannot. That's just not how it works to be able to calculate these things. We will probably end up getting answers that are close to the final answer, but it's not exact, and therefore we're getting wrong answers at the very end as well. So again, the height of these triangles, look for the line that touches at a point and touches along a side length and creates that 90-degree angle little square in there. That's our giveaway. That's going to touch the height, and that's going to touch the base. Okay? So be on the lookout for those for the area of triangles when you're working with them. The last equation that we have with triangles is just the general perimeter equation. There is nothing fancy. There is nothing advanced about this one. I am just going to take the outside side lengths. I'm just going to add all of those together. Nothing special, nothing advanced. You can write this out and then use a calculator to get to the answer. Nothing wrong with that. I recommend using a calculator for this. Regularly, we see these get advanced by them making the outside side lengths just really gross decimals. And again, let the calculator do all of that heavy lifting for you to find what that answer is going to be. But nothing fancy beyond that for the perimeter. Really isn't a whole lot that we can do beyond that. And I think we've worked with way more fancy and advanced stuff than that throughout the quarter so far. And our last shape that we have is the trapezoid. And this is a really weird one that it can give people a lot more headache than I think it needs to, but it's also just the nature of it being a really weird equation and shape in general. So we have one main new equation that we're going to be using with the trapezoid. Again, the perimeter is just going to be adding all of these side lengths together. The outside side lengths, I should say, adding all of those together. Nothing fancy about that. That's your go-to with every single perimeter in existence. The one that I want to speak to is the area equation. And I want to note this only because there are several ways that this can be represented in textbooks. They both mean the same thing, but it's just a different way of denoting it. On the homework or on the test, I will not care which one you would like to use. I would just pick one and commit to it. So our general equation follows one of these two forms, and again, we'll go through them in a bit more detail. I'm going to take 1/2 of the quantity of A plus B, A plus B being the two side lengths that are parallel to one another. And I'm going to multiply this result by the height of the trapezoid. Now, as we're noticing here, our first equation has A and B. The second equation has B1 and B2. All this does is represent, in this problem, or for this equation, A represents one of the bases, B represents the other base. If I'm looking at this second equation here, B1 represents one base and B2 represents the other base. So you could use A and B, you could use B sub 1, B sub 2, you could use X and Y. It's kind of your call, but what it's really wanting to get at is that I have two base values that I'm going to be using, and I'm going to be plugging those inside or into this set of parentheses here. Now, some giveaways and some big hints that I want to give for everyone as you are looking at trapezoids and trying to find the area with these. Similar to triangles, we have the height that is going to show up in all of these in some way, shape, and form. And this height, the vertical line that's perpendicular to these two sides, is a huge giveaway with really important information in it. So I'm trying to do this in red in the picture here, but I really want to note this because it's going to save you guys a lot of time with solving these for area. So I have the height. And once again, it has this little right angle showing up on it. That is a giveaway. That's a huge giveaway for us. So always be on the lookout for that. I'm then noting that the height is touching these two sides of my trapezoid. Now notice what these two overall, these red sides here are denoted as. This side here is listed as A, which based on one of our equations, A represents one of our bases. The side length up here is represented as B, which is the other base. So this height and where this right angle shows up, the two lines that it touches that create those right angles, those are your two bases, and that is your height right there. And you can just pull those A, B, and H values out, plug those right into the equation here, and then solve for the area right after that. And again, use your calculator to actually go through and solve those. The equation can get a little messy, but yeah, we have calculators for a reason. Let's use them for that. But that's the big hint that I want to give everyone with these trapezoids is look for that height, and then the two bases are going to be touching on the ends of that height, and it's going to make these problems way faster and way easier for you to go through. And again, it's your choice if you want to use A and B, B sub 1, B sub 2. Both work. I do not care which one you use, and I am not aware of any other math instructor who's going to care on which one you would use as well. The one thing I want to note with this picture, and mainly just to hopefully quash some ideas of there being more restrictions on this thing, this picture lists A as representing the long base and B representing the short base. This rule right here is not permanent. You could reverse which of these is A and B for the bases as much as you would want. They're going to add together the same way anyway. So don't get too bogged down or stressed in thinking, oh man, I need to identify the long side has to be this value, the short side has to be this other variable. Nope. This is one of these is the first base, the other one is the second base. Great. I'm going to add them together inside the parentheses, regardless of which one is first or second. Okay, so this is a page within our OneNote document that you guys are all more than welcome to download, save, and print out for yourself. We were running the class in person and I wasn't sick with stuff. I would be printing this out for you guys and I'd be giving this to all of you. I think we did this when we were working with our unit conversions a little bit as well. But this page is a huge and awesome summary of all or darn near all of the formulas that we have been covering. I recommend that everyone goes to campus and prints this out for yourself, or if you have a printer at home, print this out for yourself. It's a fantastic cheat sheet, as it were, of all these equations that we are using. As we're seeing with trapezoids, yet again, there's another way of denoting the two bases. So again, more flexibility there. But I think this is a fantastic tool to have for any and all of these geometry problems that we are going through and as we are covering them. So I would say if you have the time, go over to our OneNote, download this document, save it for yourself, have it up maybe in a different window as we go through some example problems, because this is everything that we have covered for equations that I can think of and that I'm seeing on my end that we'll be using for the quarter. The circle ones, we're going to be getting to those in 9.5. So more of that coming. And we're not going to be working with a lot of the 3D stuff for this particular class, but hey, it's kind of nice to have every now and then. So just wanted to note this as a resource that is available to you guys. You are welcome to download it, save it, print it out, or if you're watching this later online on YouTube, you can pause the video, screenshot this thing and then build your own version of this through Photoshop or something like that for your own cheat sheet there. So let's go ahead and jump over and take a look at some example problems using the material that we covered today. I'm going to be using the 9.4 extra practice PDFs that are created in our OneNote for these examples here. Otherwise, we get a whole bunch of extra stuff showing up in the lecture notes and it becomes a much larger document. So let's start with some of our first examples here. All we are doing is we are going to classify each triangle based on its angles and its sides. So remember, we have those. We have the equilateral, we have the isosceles, the acute, the scalene, the obtuse, things like that. So we want to take a look at these things and say, based on the angles, what kind of a triangle is it? Based on the side lengths, what kind of a triangle is it? And then we'll put those two definitions together as our final answer here. Let's look at our first example. Looking at this, and what am I noticing here? Well, I see that I have a right angle showing up, so this thing is going to, at the very least, be a right triangle based on the angles. I can write that in, so it's going to be at least a right triangle. Now I can look at the side lengths. What do I notice about the side lengths here? I'm seeing that two of these are the exact same as one another. Well, this can sometimes be denoted as having the little lines going through that. So if I have two of the side lengths that are the same, then that means, yeah, they're equal to one another. That means we are going to have an isosceles triangle. Two of the side lengths are equal, and isosceles triangle, exactly. Loving it. Chat's on fire. Keep it going. Love it. So we are going to have a right isosceles triangle. Now let's see if I can actually spell isosceles correctly. Nope, got it wrong. There we go. Right isosceles triangle. And that's all that I need to do. This thing is classified. Okay, green isn't going to show up very well. Guess I'll have to box the answer here instead. That's fine. So we have a right isosceles triangle. That is the extent of what we need to do to classify this thing. And then we're done. Let's take a look at number 2. So we're looking at this, and again, I think it's good to start with the angles, then go with the sides, but there really isn't a correct order you want to go in. You need to look and check for both of them. So what am I noticing about the angles? And I'm seeing, okay, I've got two of these or all three of them are different. Okay. One of them is a 90-degree angle. So, okay, I'm once again going to have a right triangle show up. So for the angles, I can say that this thing is right. If I look at the side lengths, none of them are the same. So that means we're going to end up having, yep, scalene triangle. Okay, perfect. Yep. So we just say this is a right scalene triangle, and bam, good to go. No extra work necessary. Done. Let's see if we can maybe, I don't know, jump away from something that is that's right triangles. We'll scroll down here a little bit, see if there's a weird one that shows up. Here we go, 17. This is a good weird looking one here.
You said that last one was a scaling triangle?
Correct. Yes, we do. We have 3 different side lengths. This 3.1, 4.2, and 5.2. So 3 different side lengths that classifies as a scalene triangle. Yeah. So again, we'll start with the angles. Looking at the angles that we've been given, what are we noticing? Okay, well, I have one of the angles is greater than 90 degrees. And that tells me right there that I have an obtuse triangle. And now we can look to the side length and see what we can get from there. What am I noticing about the side lengths with this? Yeah, it's an isosceles triangle. I have 2 of the side lengths that are the exact same thing as one another. And that is my giveaway from our definitions that I have an obtuse isosceles triangle. So I can write that in. Maybe my pen is going to cooperate. Yeah. Perfect. And there we go. That's our classification, and can't do a whole lot else beyond that. See if we might be able to do, I don't know, let's do number 16. We'll do that, and then we'll jump to some other examples with the equations. Now with number 16, again, we're looking at the angles. Is there anything that's jumping out to us there? I don't have anything that has the same angle or anything greater than 90, so this is going to therefore classify as an acute triangle. All the angles are less than 90, so I can write in acute. And then I look to the side lengths and I'm seeing, is there anything that jumps out on the side lengths? Yeah, this is scalene. None of the side lengths are equal to one another. They're all different, and that's fine. It just means that we're going to have an acute scalene triangle. And that's all we do for our final answer, and then we're good to go. And this is the extent of what I could be really testing you guys on or working with you guys on in terms of classifications for triangles. There are some more quote unquote advanced method that some people like to use with these of, oh, you need to check for these properties first or that property first and after and blah, 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 blah. We're not going to be doing anything beyond what we just did here for the class. So get comfortable with looking at the angles, get comfortable with looking at the side lengths, and then see which of those classifications for each of those we're going to be applying here. And then just put those terms together, obtuse isosceles, acute scalene, the triangle there. You can also reverse these, and there's nothing wrong with it. It just might be slightly different than what you see written out on an answer key. But at the end of the day, it still is an isosceles obtuse triangle if you were to reverse those. It would be correct. I believe the convention is normally the angles listed first and then the side length. So that's where we generally get that convention from. Okay, let's take a look at some area problems. And again, these are about the extent of the difficulty that I could give you with solving for area on tests or the homework or anything like that. The perimeter is just adding all the outside side lengths together. There's nothing particularly advanced about it. I think the area is the tricky one to go after. So we're going to start with number 49 for this. And we're going to round all of these answers to one decimal place. The program didn't automatically put that in there. On the test or on the homework, it will have that specified. And if it doesn't, default to going to 3 decimal places like we've talked about in the past. So I think it's helpful with these, starting with 49. What's the shape that I'm using? I'm using a triangle. So I'm going to just write down the general equation for the area of a triangle. We can reference our notes. We need to. The area of a triangle is 1/2 base times height. Let me clean up that just a little bit here. Equals 1/2. There we go. So I need to find the base and find the height to be able to get to this answer. I'm looking at this, and again, I'm looking for where my base is and where my height is. As I gave you guys the hint, be on the lookout for where the right angle shows up to tell you about the height of something. Now, this right angle shows up outside of the triangle. That's fine. This vertical line still denotes the height of this thing. So for what I'm going to plug into my equation, this 3.8 is going to be plugged in for the height. Now I have some dashed parts that are out here. The dashed parts we assume are just placeholder things. They are not actual values of the entire triangle itself. So what would the base be? Well, if this dotted line was actually connected to the rest of the triangle, then this side length down here is what I'm going to be using for the base. So I have my height of 3.8. I have my base of just this section over here, 8, and I can plug those into my equation and solve for the area. Okay, and I'm getting to 15.2 square inches for the area. Yeah, okay, perfect. Getting similar things in chat. Love it. And this is the extent of what we need to be doing for showing work and getting to our answer there. And I think if we get into the habit of doing this, writing out the general equation, then plugging in values for base and height, I think all of these problems get way, way, way easier over time. And then with all of the calculations that you do afterwards, please use your calculator. The decimals can get really, really gross, and I don't want you guys feeling like you need to do that by hand. We paid good money for calculators. Let's use them. Let's look at 50. We've got a trapezoid showing up with this, and I'm told to find the area. So I need to write out the equation for the area of a trapezoid. Now, as we discussed, there are multiple options that you could take to do this. I'm going to go ahead and use A and B to represent the bases, but you are more than welcome to use B sub 1, B sub 2, or X or Y or something like that, whichever one's more useful to you as you are going through this. So now I'm once again looking for my height and my two bases. Remember, the giveaway with this is to look for where is the right angle. That sits right on the height, and that height touches the two bases that I'm going to be using here. So I'm going to be using, try and do this in pink here to highlight a little bit. I'm seeing there's my right angle. That means that this line is my height. And the two lines on the end of it that it's touching, those are going to be my two bases. Which one is A, which one is B? We've got that freedom and flexibility to choose that as we want, but those are my three values I'm going to plug into this equation. We'll plug those in and calculate our answer. Okay, and I'm getting 7.5 inches as my final answer. Hey, there we go. Love it. Getting similar things in the chat. Fantastic. And this is, again, really good example of how we're going to go through and set these things up for ourselves. Doesn't necessarily matter the shape that we have been given, the thing that we are solving for. I think writing the original equation is by far the biggest game changer for ourselves as we're going through these problems. And then taking one line to actually write it out for ourselves with the numbers substituted in, that also goes a long way with these. We'll scroll down here and see if there's any other ones that stand out to us as something. Actually, you know what? Let's do 52. Let's get a parallelogram in here. It's right here. Okay, so I'm looking at 52. And again, I want to identify what sort of a shape have I been given. This thing looks like a parallelogram. Again, we're finding the area of this thing, so I want to write out the equation for the area of a parallelogram. I recommend looking at that geometry formulas page, finding the parallelogram shape, finding the area for a parallelogram on that, and then writing that out for yourself. Be sure to have the area is equal to the base times the height for a parallelogram. Now I need to determine what's the base and what's the height. Well, again, little red right angle box, that's going to be the giveaway for our height and for our base. So the vertical line that's created there, that's going to be our height. So my height is going to be 5.5. And the side that it's touching is this 18 down below here. So my base is going to be 18. I plug those in and solve for my answer. And that perfect. Love it. A lot of the same things here. Yeah. Fantastic. So 3 really good solid examples of going through and finding the area of these things. Let's look at number 114 here. I just want to get us one more look at trapezoids. I think trapezoids are ones that give people the biggest headache, and understandably so with the different bases and things like that. So once again, trying to find the area of this trapezoid that's been given to me. I'm going to start with writing out the general equation. We can reference our notes for that. I'm once again going to use A and B for this, but you are welcome to use X or Y or B sub 1, B sub 2, whichever one you would like. I'm then looking for the height of this thing, or looking for that giveaway right angle. I'm noticing, okay, have that right there. So this vertical line here is going to denote the height of this trapezoid. So I'm going to have a height of 7. I can try, so let me do this in pink here. There we go. I have my height that's going to be there, and then the 2 end things that it's touching are going to be my 2 bases. So I can plug those into my equation and then solve for the answer from there. And I'm getting 97.28 square centimeters. Ooh, did I do something wrong on this? There's a distinct possibility of that. Double checking my math here. 18. Ah, I see it. I put a 7.6 at the end also. There we go. Now I'm getting the same thing as Chad. Once again, good that you guys are keeping me honest with this stuff and double checking me. That's what we want. It's a good thing. Okay. It's pretty good. Extra example and cautionary tale. Make sure you're translating everything over correctly. Maybe it would have been helpful if I had done something like, I don't know, A equals, B equals, H equals off to the side. 7.6. So if you wanted to do something like this off to the side for yourself and then plug these values into your equation, I think that would be a great call to use to avoid the error that I just made, because very easy to do. Yeah, and something like this, I think, yeah, perfectly fine to use that on the homework or on the test as well. 118, we've got this weird, almost double triangle showing up here, right? We've got a triangle, it's in black, and then we have this dotted line triangle that's given to us also. Remember that the dotted lines are not assumed to be part of the actual shape that we are working with. The main thing that we're solving for is this triangle over here that's in black. The red is, hey, here's some placeholder stuff that could help you as you're going through the problem. Okay, we're going to reference it, but we're going to note that it's this main triangle up here that I care about. Again, I'm working with the area, so I'm going to write that out. The area of a triangle, 1/2 is base times height. And maybe off to the side, we'll try writing out base equals and height equals. See if we can avoid any errors showing up otherwise. And once again, I'm looking for this right angle to show up somewhere in there. That's going to tell me the 2 sides that are going to be my base and my height. Well, I'm noticing that this line goes up to a point here, a vertex. That tells me that my height is going to be 9.4 centimeters. And I can just fill that in right off to the side. The side that it would be touching at the bottom here, this is going to denote the base. So I have a base of 7 for this particular problem. And then the big question I think that shows up for a lot of people is, well, hold on, what am I going to do with this 14 centimeters here? I've got this other side length. Could I do something with that? And great, I have another side length, and that's nice and all. It doesn't fit anywhere into our equation. So this is just extra information that's kind of nice to have, but absolutely irrelevant in actually solving for the area here. So we can ignore it entirely. I plug these values in, and I solve this out to see what the area is. And I'm getting 32.9 centimeters. Hey, there we go. Get the same stuff elsewhere. Love it. This is pretty much the extent of what I can and could be asking you guys with regards to the area for problems on the test or anything like that. Um, I think whether you're solving for the area, you're solving for the perimeter, whatever it might be for a shape, determine first and foremost, what is the shape that I'm working with? What is the very specific thing that I am solving for? And then after that, plug things into that equation and solve for whatever is missing from there. We have all the tools that we need to solve for a single equation or a single variable. We've been doing that all quarter long, and we just solve it out that way.